Okay, this is supplemental information for Dynamics Lecture 1 and going into Lecture 2. So I thought that what I would do is, because time is short during the lecture, we only have 50 minutes 3 times a week, and I don't usually get through all the examples I want to go through. I could if I went through them at a lightning pace, but I don't want to do that. So I thought maybe as an alternative, I would post some examples that ordinarily I'd do in class if we had more time so that you can look at them if you so desire or not. I think they'll be helpful though, because I chose examples to do that are similar to both the homework and to what we're talking about in class. So we're starting again with rectilinear motion. So recall that rectilinear motion is just motion in a single direction. And so for our motion in a single direction, we're also looking at variation in acceleration. Now recall that acceleration comes in 3 forms. You can have acceleration as a function of velocity, acceleration as a function of position, and acceleration as a function of time. So I'd recommend is go back and look at that table that I posted in lecture 1 that lists the 3 different types and how the derivatives of dv dt and dx/dt are manipulated so as to figure out the equation. So in this example, we have a particle moving along a straight line. It's subjected to deceleration. Now we're told that the acceleration is equal to minus 2v cubed meters per second squared, when v is 8 meters per second and the position equals 10 meters. Sorry, it's a little out of focus, and time is 0. So we're going to call our axis or our beginning 10 meters. This is where we're starting, even though it's back here, would be 0. And at that point, we'll imagine the particle's already started to move. It's moving. It hits this point, and now it's slowing down. So it's at a velocity at that point here of 8 meters per second, and we're going to call it time 0. So what we want to determine is what is the velocity and position. I'm using s in this case as opposed to x, and I will vary that depending on the source I get, but s is the position at t equals 4 seconds. So the first thing we need to consider doing any type of this problem is first off say, okay, well, I know acceleration is given as a function of velocity. All right, so I know that a equals v dv ds. And that just comes from the equation a dx equals v dv, right? So xs, same, it's the same variable. So ads, adx. So we derived that in class. And so it's very easy to figure out, but so we're going to use this relationship. So knowing that, then we're going to start by manipulating the equation so that it looks like this. ds equals v dv over the acceleration. And you can see where we're going to go with this because we have this as minus 2v cubed meters per second squared. So if we set up our integral, what's it going to look like? It's going to have from 10, because that's our starting point, to s and ds, and that is going to equal our point of 8, because we're at 8 meters per second, to our v. Sorry, it's kind of squished in there. Sorry about that. And then that is going to be minus v dv all over 2v cubed. So the minus sign just comes from there. So I just distributed it there. So there's our relationship. Now we're going to integrate. Now, you may ask, why did we use this expression first? Well, we knew we needed to find a position. So we may as well start out there, and then later on we can manipulate to find time, and we'll use a different one for that. So if I integrate this, what do I get? Well, that just becomes s, so it becomes s minus 10, and then that is going to equal 1 over 2v minus 1 over 16. So how did I get that? The v canceled with the v cubed to be v squared, and then if you integrate v to the minus 2, it becomes v to the minus 1. The negative 1 disappears, and the 1/2 times 8 gives us the 16. So you have 1 over 2v minus 1/16. So we can manipulate this equation so that we get it in terms of v. So s minus, if I manipulate it, I get s minus 10 plus 1, plus 1/16 equals 1 over 2v. And then that's going to give me s minus 160 over 16, converting 10 to that, plus 1/16 equals 1 over 2v. Sorry, getting off the page there. So finally, if I subtract those off, multiply both sides, I end up with 100, and I end up with 16s minus 159 equals 8 over v, or finally v equals 8 over 16s minus 159. Now, of course, we're not done yet. What we have to do now is, even though we started with dVds, we ended up with position in as a function of velocity, and that's where we're at. So if we take this now and we look at, let's split the page, and we say, okay, well, we know that ds dt is equal to velocity, right? Dx dt is velocity. So we can also write this as dt equals ds over v. So then we integrate 0 to t, and that's going to give us the equivalent of, from 10 to s, 1/8, 16s minus 159 ds. All right. So we end up now with, afterwards, we end up with t on one side, and that equals what? Pull the 1/8 out, get integral from 10 to s of 16s minus 159 ds. And then lastly, we get 8t equals 8s squared minus 159s, evaluated from 10 to s. Okay. So we can then fix that up after we plug everything in to get 8t equals 8s squared minus 159, s, minus, and then that's going to be a minus a 800 minus 1590. So basically evaluating 10 here is 800, and 10 there is 1590. So that's where it comes from. So in the end, you can see what this is going to look like. It's going to end up being a quadratic, and that's what we're going to have to do. And so that's the one little trick in this problem, is we're going to now fix this so that's 8t equals 8s squared minus 159s plus 790. All right. Now, we do end up with the quadratic. So we look at it as because we have s and we have t, well, how are we going to solve it? Well, remember, what is our time? Our time is 4 seconds. So if we plug 4 into here and simplify, we get basically 32 over there that then comes over here. And we end up with 0 equals 8s squared minus 159s plus 758. Okay, so there's our quadratic. So far, so good. Now, I went through steps that sometimes I may not have to, and I'm sure you guys, you're less rusty with calculus than I am, so you would have seen all these steps. But the main takeaway, of course, is manipulation of this to get to this, follow through here, and you know, I think I skipped one step here, but this is all simple algebra. So if it's helpful, pause it, try to do it yourself. And I would encourage you to, is when I show the problem initially, you know, depending on how dedicated you are, spend some time figuring out how would I do this problem, and then go and look at the solution. You'll be much better off in the long run if you do that. Okay, so we have that, and so we'll go ahead and solve our quadratic. So we end up with s equals, run out of space, but we end up, when we solve the quadratic, we get s is equal to 11.93 and 7.93. All right. Well, we know it can't be 7.93 because we started at 10, so it has to be 11.93. So if we draw a line, what we're saying is that here's 10 meters at 11.93 meters. That's where the particle will be at 4 seconds. And then the final question is, what is the velocity? So, well, we know the velocity because remember, we have a statement for velocity that we found back here. So remember this. So the velocity is based on position, which of course is based on the initial deceleration. So if we plug in 11.93 for this, we get velocity equal to 8 over 16 times 11.93 minus 159, and that gives me a value of about 0.250, or a quarter meter per second. All right. So I hope that makes sense. Again, this is supplemental information. I'm going to try to do as much as I can. It does take a little extra time. I don't have time to edit the video to make it picture quality, but bear with me. So I will continue with a couple more examples, and I'll post these on Canvas so you can hopefully get a little extra help if needed. Thank you.